When working with an ungrounded 208 volts to 480 volt system, prioritize safety. Ensure the system is properly labeled and isolated and use personal protective equipment. There are three main options for wiring such a system. Firstly, leaving it ungrounded. Secondly, corner grounding. And thirdly, using transformer isolation. Leaving the system ungrounded is a common approach. It provides no intentional grounding path for fault currents. It requires careful selection of equipment rated for ungrounded systems. Corner grounding involves grounding one phase of the system at a single location, typically at the transformer secondary. It provides a path for fault currents to flow back to the source and may require special corner grounding transformers. Transformer isolation involves using an isolation transformer to create an isolated grounded system on the secondary side. It provides a grounded neutral reference and reduces the risk of ground faults. This option is typically more expensive than the other two. For most applications, corner grounding is the recommended option as it provides a path for fault currents and reduces the risk of arc flash hazards. Ground fault protection devices should be used to detect and interrupt ground faults. Equipment should be rated for ungrounded or corner grounded systems. Maintenance and inspection should be performed regularly to ensure the integrity of the grounding system. Special corner grounding transformers are available to provide isolated neutral ground for ungrounded systems. These transformers have a delta primary and a grounded Y secondary. Selecting the appropriate wiring method for an ungrounded 208 volts to 480 volt system involves careful consideration of safety, cost, and application requirements. Leaving the system ungrounded is the simplest approach, but it offers no protection against ground faults. Corner grounding provides a path for fault currents but may require special equipment and careful installation. Transformer isolation offers the best protection against ground faults but is the most expensive option. When making your decision, consider these factors: firstly, safety; secondly, cost; and thirdly, the specific requirements of the application. Let's delve deeper into each of these wiring options. Firstly, let's discuss leaving the system ungrounded. In an ungrounded system, there is no intentional connection between the electrical system and the earth. This means that if a fault occurs, such as a short circuit to ground, there is no path for the fault current to flow back to the source. As a result, the voltage on the unfaulted phases will rise, potentially damaging equipment and creating a safety hazard. Ungrounded systems are sometimes used in applications where continuity of service is critical, such as in hospitals or industrial plants. In these cases, the ground fault can be tolerated until the next scheduled shutdown, at which point the fault can be repaired. However, ungrounded systems are generally not recommended for most applications due to the increased risk of equipment damage and safety hazards. Secondly, corner grounding. Corner grounding involves connecting one of the phase conductors to ground at a single point, typically at the transformer secondary. This creates a path for fault currents to flow back to the source, allowing ground fault protection devices to detect and interrupt the fault. Corner grounding offers a good balance of safety and cost and is suitable for a wide range of applications. However, corner grounding can create voltage imbalances in the system which can damage sensitive electronic equipment. Also, corner grounding requires careful installation and maintenance to ensure that the grounding connection remains intact. Thirdly, transformer isolation. Transformer isolation involves using an isolation transformer to create a separate, isolated electrical system. The primary side of the transformer is connected to the ungrounded 208 volts to 480 volts system, while the secondary side is connected to a grounded system. This provides a number of benefits, including firstly, a grounded neutral reference. Secondly, reduced risk of ground faults, and thirdly, improved power quality. Transformer isolation is the most expensive option, but it offers the best protection against ground faults and other electrical problems. It is typically used in applications where safety and power quality are critical, such as in hospitals, data centers, and industrial plants. Ground fault protection devices, or GFPDs, are essential components of any electrical system. They are designed to detect and interrupt ground faults, which can cause equipment damage, fires, and electric shock. There are two main types of GFPDs. Firstly, ground fault circuit interrupters, or GFCIs, and secondly, ground fault relays, or GFRs. GFCIs are typically used in residential and commercial applications to protect people from electric shock. They are designed to trip when a ground fault current of 6 mA or more is detected. GFR are typically used in industrial applications to protect equipment from damage. They are designed to trip when a ground fault current exceeds a certain threshold, which is typically adjustable. When selecting GFPDs, it is important to choose devices that are compatible with the wiring method used in the system. For example, GFCIs are not suitable for use in ungrounded systems, as they require a grounded neutral reference to operate properly. It is also important to choose GFPDs that are rated for the voltage and current of the system. In addition to selecting the appropriate wiring method in GFPDs, it is important to ensure that all equipment used in the system is rated for the voltage and grounding configuration of the system. For example, equipment used in an ungrounded system must be rated for ungrounded systems. Similarly, equipment used in a corner-grounded system must be rated for corner-grounded systems. Using equipment that is not rated for the system can lead to equipment damage and safety hazards. Finally, regular maintenance and inspection are essential to ensure the integrity of the grounding system. This includes inspecting grounding connections for corrosion and tightness, testing GFPDs to ensure that they are operating properly, and measuring ground resistance to ensure that it is within acceptable limits. It is also important to keep accurate records of all maintenance and inspection activities. Special corner grounding transformers are available to provide an isolated neutral ground for ungrounded systems. These transformers have a delta primary and a grounded Y secondary. The delta primary is connected to the ungrounded 208 volts to 480 volts system, while the grounded Y secondary provides a grounded neutral reference. This allows the use of GFPDs and other grounded equipment in the system. Corner grounding transformers are typically used in industrial applications where it is necessary to provide a grounded neutral reference for an ungrounded system. The NEC, or National Electrical Code, provides detailed requirements for the design, installation, and maintenance of electrical systems. It is important to consult the NEC when working on any electrical system, including ungrounded 208 volts to 480 volt systems. The NEC contains specific requirements for grounding, overcurrent protection, and wiring methods. It also contains requirements for equipment labeling and safety. Failure to comply with the NEC can result in fines, penalties, and even criminal charges. Grounding is a critical aspect of electrical safety. It provides a path for fault currents to flow back to the source, allowing ground fault protection devices to detect and interrupt the fault. Grounding also helps to reduce the risk of electric shock by providing a low-impedance path to ground. The NEC requires that all electrical systems be grounded in accordance with its requirements. The specific grounding requirements vary depending on the type of system and the application. Overcurrent protection is another critical aspect of electrical safety. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect equipment and wiring from damage caused by overcurrents. Overcurrents can be caused by short circuits, overloads, or ground faults. The NEC requires that all electrical systems be protected by overcurrent protection devices in accordance with its requirements. The specific overcurrent protection requirements vary depending on the type of system and the application. Wiring methods are the techniques and materials used to install electrical wiring. The NEC specifies the types of wiring methods that are permitted for use in different applications. The NEC also specifies the requirements for the installation of wiring methods such as conduit fill and support spacing. Proper wiring methods are essential to ensure the safety and reliability of the electrical system. Equipment labeling is another important aspect of electrical safety. The NEC requires that all electrical equipment be labeled with information about its voltage, current, and other important characteristics. This information helps to ensure that the equipment is used properly and safely. Safety is the most important consideration when working on any electrical system. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself from electric shock and other hazards. Before starting any electrical work, be sure to firstly de-energize the circuit, secondly, use appropriate personal protective equipment, and thirdly, follow all safety procedures. If you are not qualified to perform electrical work, hire a qualified electrician. Working with ungrounded 208 volts to 480 volts systems requires a thorough understanding of electrical principles, safety practices, and applicable codes and standards. Whether you choose to leave the system ungrounded, implement corner grounding, or utilize transformer isolation, prioritizing safety and adhering to best practices is essential for ensuring a reliable and safe electrical installation. Always consult with qualified electrical professionals for the design and implementation of any electrical system to ensure compliance with regulations and optimal performance. This comprehensive approach will help mitigate risks and provide a secure electrical environment for all users and equipment connected to the system. Moreover, ongoing education and training in electrical safety and best practices are crucial for all personnel involved in the operation and maintenance of electrical systems. Staying informed about the latest advancements in electrical technology and safety standards will enable you to make informed decisions and implement effective measures to protect against electrical hazards. By fostering a culture of safety and continuous improvement, you can create a workplace where electrical risks are minimized and the well-being of all individuals is prioritized. Remember, electricity is a powerful force, and it should be treated with respect and caution at all times.